We hear it all the time. The future is renewable. But it always comes with that one tricky question. What do we do when the sun goes down or the wind just stops blowing? Well, let's dive into the pretty surprising fix for one of the biggest challenges in energy today.
That's the big one, right? It's the fundamental question we have to answer if we're serious about a green energy future. Solar and wind are amazing, but they're not always on. That up and down nature, the intermittency, that's the central puzzle we've got to solve.
So let's really break down this core challenge. How do you build a totally reliable grid on top of fundamentally unreliable sources?
The obvious answer just seems to be, well, build a giant battery, right? You store all that solar power from noon and then use it at midnight. Simple. But, and this is where this research gets really fascinating, the best solution is way more clever and way more complex than just building one big box.
Yeah, it turns out the solution isn't one single type of battery at all. It's actually more like a tale of two very different kinds. Let's see how the energy system model uses completely different tools for completely different jobs.
So on one side, you've got your electric batteries. They are super efficient, you get most of the energy back, and they're really cost-effective if you're charging and discharging them every single day. On the other side, you have hydrogen. Now, it's way less efficient. You actually lose over half the energy in the process, but, and this is the key, it is incredibly cheap to store in huge amounts for a long, long time. We're talking days, weeks, even months. And this right here illustrates their roles perfectly. Just look at these heat maps. The battery, up top, shows this sharp, predictable daily pattern. It charges up in the bright yellow midday sun and discharges every single night. It's a sprinter. Hydrogen, down below, is a total marathon runner. Its pattern is way less regular. It's responding to big, multi-day weather systems, smoothing out those long, windless streaks in the middle of winter.
Now, what's really interesting is how the model actually places these technologies. It's not random. It puts the batteries, our daily sprinters, down in the sun-drenched south of Europe to just soak up all that solar. And it puts the long-duration hydrogen storage way up in the windy north to balance out those powerful but variable offshore wind farms. It's a perfect marriage of technology and geography.
So, problem solved, right? Batteries in the south, hydrogen in the north. Easy.
Well, not so fast. Just when we think we've got it figured out, the paper reveals this powerful twist that kind of changes the entire equation.
And this secret weapon is a concept called sector coupling. Now, it sounds a little technical, but the idea is actually pretty simple. Instead of treating electricity for our lights, fuel for our cars, and gas for our heaters as totally separate problems, what if we connected them all into one intelligent, integrated system?
As you can see on this map, right now, these different energy demands all live in their own little silos. You've got electricity in black, heating in orange, and transport over here in light blue. Sector coupling is all about smashing those silos and linking everything together.
So let's see what actually happens when we connect these sectors in the model. Because this is where things get really surprising.
Okay, first let's look at our baseline. If we only decarbonize the electricity sector, you can see here we need a decent chunk of dedicated batteries. That's that yellow slice, plus a whole lot of hydrogen. This is our starting point. Now keep your eye on that yellow slice. When we connect the transport sector by switching over to electric vehicles, poof, it's just gone. It completely disappears. Why? Well, we don't need to build all those extra stationary batteries anymore because we can just use the millions of batteries that are already sitting in our cars. And the scale here is just staggering. Electrifying all of Europe's cars creates this giant distributed battery with 6.1 terawatt-hours of capacity. That is enough to power the entire continent's average electricity needs for 19 hours straight. We're not building a new battery, we're just plugging in the ones we already own. And it's a very similar story for heating. When we connect the heating sector, the model starts building massive amounts of thermal storage. You can basically think of them as giant, super-insulated hot water tanks. And this is an incredibly cheap way to store all that abundant solar energy from the summer and then use it to heat homes in the dark, cold winter.
So let's zoom out. What does this all mean for the big picture? The key takeaway here isn't just about finding clever new technologies, it's about understanding when we actually need to deploy them.
What's so fascinating here is that for the first 60, even 80% of CO2 reduction, we barely need any new storage at all. The need for these huge, expensive investments only skyrockets at the very end of the journey, as we're pushing toward 95% decarbonization. So by using sector coupling, we push that really steep, really expensive part of the curve as far into the future as we possibly can.
So what you end up with is this beautifully synergistic system. Our cars become the daily battery, balancing out the sun. Hydrogen acts as our multi-day backup, smoothing out the wind. And thermal storage becomes our seasonal workhorse, moving summer's heat into the winter. The cheapest path forward isn't building one giant battery. It's building a smarter, more connected system.
And that really leaves us with a final thought. Perhaps the biggest challenge in the energy transition isn't an engineering problem of inventing better storage, but a systems thinking problem of intelligently connecting all the pieces that we already have.